We're going to continue now with exit ticket 16.3, looking at acids and bases through the lens of equilibrium. So you know that the definitions of acids and bases, and we've been basically teaching you that acids have H plus associated with them and bases are OH minus associated with them. We're going to take it a few steps further today. We're going to talk about amphoteric water, strong acids, strong bases, and weak acids. We're going to stick to the strong acids and bases today, and we'll save weak acids and weak bases for another talk. And we're going to get to pH. So water's an acid, and as a base, as we talked about, acid-base reactions take place in aqueous solutions, and because water can act as an acid or a base, we call it amphoteric. It self-ionizes in an equilibrium. So I want you to notice the way we've written it here is H2O plus H2O gives us H3O plus and OH minus. So this hydronium cation is also written as H plus in the way we think about it in acid-base systems. So we've got hydronium and hydroxide. Because this is an equilibrium, we can write an equilibrium constant for it. This is something you have to get down. The equilibrium constant for this system is called Kw, and at 25 degrees Celsius, if you multiply the H3O or H plus concentration in moles per liter times the OH concentration, the hydroxide, in moles per liter, it always equals 1 times 10 to the minus 14th at 25 degrees Celsius. This 10 to the minus 14th is a really important number to notice, but what I want you to get is if you have this number as a given, if you divide any concentration into it, it solves for the other concentration in that equation. So in any aqueous solution at 25 degrees Celsius, the product of H3O plus and OH minus must always equals 1 times 10 to the negative 14 at 25 degrees Celsius. In any aqueous solution, it's possible to determine the amount of acidic or basic substances using that equation. This equation. Again, I hope you have it written down on your exit ticket because we're going to use it at the chart that's at the bottom of the front page of the exit ticket. Let's see, that's the same thing. One thing to notice that in pure water, that's the pH is 7 because it's neutral. The H3O ion concentration equals the OH minus ion concentration. They will each equal 1 times 10 to the negative 7th because 1 times 10 to the negative 7th times 1 times 10, let's do this, 1 times 10 to the negative 7th times 1 times 10 to the negative 7th equals 1 times 10 to the negative 14. This is why water is considered neutral. The amounts of H3O plus, the acid, and the amount of OH minus, the base, are the same. They're both minus 7. Acid solutions versus base solutions. If you have more hydrogen ions or hydronium ions, it's an acidic solution. So we're going to be comparing the concentrations of those two items. In the aqueous solution, if the amount of OH minus is greater than hydronium or hydrogen ion concentration, it's basic. These are base ions, so it'll be a basic solution. If they're equal, the solution is neutral. So now we're going to look at some numbers. We're going to do a little math. So you're going to get your calculator, and we're going to use this value. And we're going to divide that into 1e negative 14. So we're always going to type this in first. 1 times 10 to the negative 14th divided by, in this case, 1e minus 5. And that'll give us the OH ion concentration. In this case, you should get 1e negative 9. So we can see that negative 5 versus negative 9, that the hydronium or hydrogen ion concentration is greater than the OH ion concentration, so we're going to call this acidic. The next one, again, we're going to take 1 times 10 to the negative 14th divided by 1 times 10 to the negative 3, and we're going to get 1 times 10 to the negative 11. That's a tiny number, and that's a tiny number, but it's bigger. So we've got more OH ion concentrations, so it's basic. So you can go on, again, using just 1 times 10 to the negative 14th divided by the number you're given to fill this in, and then look at the two numbers and see which one's greater. If something in this column is greater, it's an acid. If something in this column is greater, it's a base. simplifying the numbers, because concentrations are so small, they're all something times 10 to the minus something, it's easier to deal with them using a logarithmic scale. So they came up with something called pH, where H is the hydrogen ion concentration, known as the hydronium ion concentration. So the pH is the negative log of H3O concentration for any aqueous solution. So now we're going to get our calculator ready, and here's what you're going to type. If you know the concentration of H3O plus or H plus, that's what you're going to plug in here. You're going to type in your negative, not minus, but the plus minus sign, negative, negative, and then find your log button, and then type in your concentration and hit equals, and it will give you a value for pH. We're looking at these exponent numbers, and we're making them into these whole positive numbers. So let's see what that looks like. If we have 1 times 10 to the negative 9, and we want to find the pH, we type in the negative sign, not minus, but negative sign, negative, and then hit the log button, and then type in 1e negative 9 and hit equals, and you're going to get a 9. The negative log is basically finding a way to look at this exponent as a whole positive number. So this one, we can just look at it and predict that when we do the calculation, our number will be 4. But let's check it. Take the negative log of 1e minus 4, hit enter. Hopefully you got the number 4. So you can sort of eyeball what the pH is going to be just by looking at the log, or the exponent of the hydrogen ion concentration. This one should be something around 8. This should be something around 12-ish. So let's see what we get. We're going to type in negative log 3.5 e negative 8, enter, and get 7.46. This is kind of close to 8. And then we're going to do this one, negative log 7.2 e negative 12, and this is 11.14. Oops, sorry, 14. So this is basic. This is acidic because it's less than 7. This is just above 7. It's slightly basic. And this is very basic because 7 is neutral and anything lower than 7 is an acid. Now let's take a look at that. Anything lower than 7 is an acid because the hydrogen ion concentration is getting bigger. The exponent's getting smaller, which means the concentration is getting bigger. So let's put this all together. pH equals the negative log of the H3O ion concentration. If you know concentration of the H plus or H3O plus, but you don't know the OH, you can use this relationship at 25 degrees Celsius. You'll divide either one of them into 1e negative 14 to figure out the other concentration. The POH, the homework will ask you to do this, is the negative log of the OH concentration. Maybe you have to go through this relationship first to find the OH concentration and then plug it into here. But here's something cool. The pH plus the POH equals 14. The 14 comes from here. So if you know the pH is 4, then you know the OH concentration is 10, because 4 plus 10 equals 14. It's pretty nifty how it all goes together. If the pH is greater than 7, it's basic. If the pH is less than 7, the solution is acidic, because that is a direct relationship with the ion concentration. If the pH is 7, the solution is neutral. Both of them have a concentration of 1 times 10 to the negative 7th, both the H plus and the OH minus. So, if you want to find the concentration of something, either the H3O or the OH minus, use the pH or the POH and use the inverse log function on your calculator. And that's what you would do, and we'll work on that in class. So we could fill out this chart, but I don't think we need to. Where are the acids? There was a place I wanted you to have a list of acids. I guess I didn't get to it here. Let's scroll down and get that list real quickly. Oh yeah, some acids dissociate in water into their ions very easily. For these acids, there's no equilibrium between reactants and products. 100% of the H pluses will come off that acid. After the reaction, virtually only products remain, and these acids are considered to be strong acid. So there's a difference between concentration, which is number of moles per liter, and strength, which is how many of the H ions come off of an acid. Here are the strong acids that you have to know. So get these written down on your exit ticket number 16. HCl, HBr, HI, HNO3, HClO4, and H2SO4. And we'll just call it quits for this presentation and pick it up here next time.